All right, let's jump right into this explainer. Ever wonder how your device has managed to remember everything the second you cut the power? Today, we are taking a fascinating, microscopic journey straight into the physical architecture of flash memory. We're going to zoom in level by physical level to see exactly how microcontrollers lock down and permanently store our data. To set the stage, I absolutely love this wonderfully colorful contrast between temporary RAM and permanent flash memory from our source material. It describes RAM as just come and go, use and throw, whereas flash memory is forever, until death. It's a slightly dramatic but super accurate way to highlight that if you actually want your data to survive turning the device off and on again, you rely entirely on flash. So here is our game plan for today. We'll start with RAM versus flash memory, move on to the flash memory die, break down blocks, dive into sectors and pages, and finally go right down to the word.
Okay, part 1, RAM versus flash memory. Let's establish the foundation. Think about your processor's main workspace. That's the RAM. It's the primary space your CPU directly accesses to do temporary work. Say you type 2 plus 3 into a system. The 2, the 3, and the command to add them all go straight to the RAM. But the literal millisecond the power cuts out, that workspace is wiped totally clean. Flash memory, on the other hand, is the permanent lifetime vault. It holds your device's core operating software safely intact, no matter what happens to the power.
See, when your code is actually running, the CPU executes this continuous, rhythmic instruction cycle, basically treating the microcontroller like a wildly intricate switching device. It fetches instructions from the RAM, decodes what the format means, and then executes it by enabling very specific physical circuits. It's just millions of tiny transistors switching on and off. But for those instructions to even be ready to load into the RAM in the first place, they absolutely must be stored permanently inside the flash.
Moving on to part 2, the flash memory die. This is the macro level.
At the very top of our flash memory hierarchy, we have the die. Some people also call it a bank. If we map this out using a city analogy, the die is the entire city limit. It's the individual physical silicon chip encapsulated inside a package. Think of that 8 GB or 16 GB thumb drive sitting on your desk right now. That physical boundary is the die. And as you can see mapped out in the physical structure here, that single die, or bank, actually encapsulates every other level we are about to explore. It's the absolute outer limit of our memory landscape.
Which brings us to part 3, blocks, the erasable units.
Keeping with that city analogy, if the die is the city limit, a block is a specific neighborhood. And blocks have a really strict, honestly kind of fascinating rule in the physical world of flash memory. They are the largest erasable unit. When you want to delete data, you generally can't just pick and choose one tiny piece of information to delete. You have to erase memory one whole block at a time. It is a massive bulk operation.
Now, a quick side note on modern setups, we actually divide these neighborhoods up. We've got P blocks, or programmable blocks, which are specially designed so software can execute directly from the flash without needing to be copied over to RAM first. On the flip side, we have D blocks, or data blocks. Those are strictly for storing information. There is no way you can run a program inside a D block.
Okay, section 4, sectors and pages, the micropartitions. Let's zoom into that neighborhood block. This is where we find sectors. In our map analogy, a sector is basically an individual street. Now, while NAND flash mostly erases at that big block level we just talked about, in a lot of NOR flash architectures, the sector actually serves as the smallest unit that can be erased. So a single block will usually contain multiple distinct sectors. And right there on the street, we have the page. Think of it as an individual house. This is where the rules flip. Erasing data is a bulk operation, right? But writing data? Totally different story. Data must be written page-wise. The page is literally the smallest unit that can be programmed. You just cannot write anything smaller than a page.
So here's where the fundamental rules of the realm get really interesting. Erasing is a massive, blunt force operation. You are wiping out whole neighborhoods or streets at the block or sector level. But writing? Writing is a super precise, targeted operation happening specifically at the page level. Imagine trying to update just a single address, but the rules say you have to write to an entire house all at once, and if you make a mistake, you literally have to bulldoze the whole block to clear it out.
You can literally trace this nested hierarchy right here. Notice how we drop deeper and deeper in. We start from the entire die, move into block 0, block 1, block 2. Open up a block and we find sectors S0 through S3.
And finally, inside those individual sectors, we find multiple pages.
All right, part 5, down to the word, our final zoom.
If our page is the house, then the word is the individual room inside that house. This is the ultimate final destination for our binary data. It's the absolute smallest configurable data element living inside a page.
But here's the kicker. A single word doesn't have one universally fixed size. The dimension of this room totally depends on your specific microcontroller's architecture. Got an 8-bit microcontroller? Your word is 8 bits, or 1 byte. Working with a 16-bit processor? It's 16 bits. And if you're on a 32-bit system, your word is exactly 32 bits.
Pulling it all together, just look at the beautiful nested logic of how physical hardware actually organizes digital data. We started at the city, our die or bank, zoomed into the neighborhood, the block where the bulk erasing goes down, to the street, the sector, down to the house, the page where all that precise writing happens, and finally into the room, the word, the foundational data unit that scales perfectly with your processor's power.
So I'll leave you with this final thought. Do you actually know the word size of your own device right now? Have you ever dug into your microcontroller's memory reference manual? Because true confidence in configuring flash memory only comes from understanding these exact nested parameters for the chips that are running your world. Dig into those manuals, understand your architecture, and I guarantee you'll never look at a basic flash drive the same way again.